Okay, just going to go through this test for some people that asked. This question right here, you hang a mass on a string and pull it down to start the system oscillating. Next, you measure the period of the resulting motion of the mass of this spring. Which of the following changes would decrease the period of oscillation? So there's only actually two, I think, that would change it. So if you look at B, pull it down with a smaller amplitude, that's not going to affect it. Look at C, compress the spring rather than pulling it down, that's not going to affect it. So you didn't even know what he does to decrease it, just whatever changes it would work here. A and D are the only ones that would change it, so that's why they have to be the answer. And they would both decrease it if you look at the math equation for it. All right, this one a little bit tricky. So the simple harmonic oscillator attached to the support, the mass is pulled from equilibrium to a position a distance a in the negative y direction. So you got to understand for this when you're matching these graphs that it's pulled down into the negative. So my position has to start at a negative position. That unfortunately leaves A, B, D, and E all as answers. All right. Then I would next say to myself, my velocity my velocity has to be zero to start because when my position is at the maximum, my velocity is zero. So that leaves E and D only as an option, where my velocity starts at zero. And then lastly, because I'm starting at the negative position, I'm going to be moving upward. So since I'm moving upward, my velocity has to be positive as I start, like zero, then becoming positive. So that's why D has to have the answer. It has the negative position to start, a zero velocity to start, and then the velocity goes positive, whereas in E, the velocity goes negative. So E would have been an example if the ball was starting at the top. D is the correct answer because the ball is starting at the bottom like that. All right. These next two questions go for this one. All right. So it says, sorry, I'm kind of wobbling, holding my phone, looking at it. A block on a horizontal frictionless plane is attached to a spring. The block oscillates along the x-axis with simple harmonic motion of amplitude A. Which of the following statements about the block is correct? All right. So what has to be correct at any of these are right. What's the answer here? At x equals a, its acceleration is a maximum. Is the right answer, right? Which of the following statements about the block is correct? At x equals a, yeah, okay. So x equals a, or negative a would have been fine. But at x equals a, the acceleration is a maximum. That's when the force is the max. Remember, the force is max, the acceleration is not. At x equals, if you look at C going backwards, x equals a, velocity is the maximum. Nope, x equals zero. Velocity equals zero at a. At x equals a, the displacement is the minimum. No, that would be maximum displacement. At x equals zero, its acceleration is the maximum. No, at x equals zero. If you think about Hooke's law, F equals kx, acceleration would be zero, because force would be zero. Which of the following statements about energy is correct? I think this one, the potential energy of the spring is at a minimum at x equals zero. That is the correct one, answer A. And that's because if you think about elastic potential energy, 1/2 kx squared, when x equals zero, you have zero potential energy, all right? And there's no height involved, so it's only elastic potential. Select the correct answer for this one. So all you have to do with this one definitely makes it look harder than it is. It gives you the mass. You had to find the spring constant. So if the equation is T equals 2 pi times the square root of m over k, the only variables in there that aren't constants are m, k, and period. You're given m, you need to find k, so then in order to get k, you need to know the period t. So all you have to do is look at this graph and find the period based on the graph. So if this is a maximum point right here, this is where the wave would start. This is half of a period, and then up to here would be a full period. So from here to here is, if you look on the very bottom part, 1.6 seconds. You might not be able to see it, but the period is 1.6 seconds. Then you just have to do the math. So you could have made an algebra mistake possibly, but you had to do the math where the period is 1.6. So it would be 1.6 equals 2 pi times the square root of m over k, and m was 2. So you had to do some algebra there to solve for that, something that, I know some of you guys were having trouble with the algebra in that equation, but that's where that one came from. No, is that it? Oh, no. Oh, gosh, when I shuffle the order, the name and period goes out of order. Whoopsies. Select the correct answer for this one. All right, this one is finding the spring constant K. So you would just write an equation for this, saying that when it is maximally stretched out here, at a maximum stretch point, let's say I pull it back, yoink, and I pull it back like that, then the energy there is 1/2 kx squared. When I release it and it goes through equilibrium, all of the energy is kinetic, 1/2 mv squared. So you would have 1/2 mv squared equals 1/2 kx squared. The 1/2s would essentially cancel out. You would divide by the a squared. In this case, x is your a. Like the distance you stretch it is the amplitude a. So that's why the answer would be D, mv squared over a squared. For this one, select the correct answer. A particle oscillates up and down in simple harmonic motion. Its height y as a function of time t is shown. At what time t does the particle achieve its maximum positive acceleration? All right. So this is a position versus time graph here, and it's saying when's the maximum acceleration. All right. One way you could think about that was I just said, like, kind of simply, I said that the acceleration graph would always be the mirror image of the position graph. So if that's the case, the mirror image would say when this position is a minimum at 1, well, when it's a negative like that at 1, that positive acceleration will be a maximum at 1, all right, because they're a mirror image of each other. So you can look at your notes for that to see what I'm talking about with the mirror image thing, but the acceleration would have to be right there as a positive. Right. And I think this might be the last one. Yep. Select the correct answer. A simple pendulum is constructed by attaching a mass m to a thin rod of length L. The pendulum is pulled back to some angle theta. Which of the following techniques could be used to change the frequency of this pendulum? So this is just saying, just what affects the pendulum is all it's saying. M does not affect the pendulum. L does, and theta does not. So the only answer is 2. So then the answer on this question is C, 2 only. All right, and that is the test questions for those of you that asked. Yeah, and that is that. Bye-bye.